Hello everybody, today we are going to talk about continuous functions, continuity. The examples are taken from Thomas's Calculus. I have put a link in the comments in the YouTube, under that YouTube video. Please download the book, it's freely available for download. And we are going to go through some examples and do some exercises in chapter 2. So continuous functions, if there is a number, a real number c on the x-axis, a continuous function would be as limit as x tends to c, the function fx should be equal to fc. And this, remember, should be a real number. And then that's the first condition. The second condition is limit as x tends to c from the positive side, fx would be equal to fc. So they are the same. And 3, limit as x tends to c from the negative side, fx would be equal to fc. This should be c. Sorry, maybe I should make that clearer. So that should be c. So they should be equal. Now let's take this value. This is a real number on the x-axis. As x tends to c from the positive side and as x tends to c from the negative side, you see that they tend to fc. So limit of fx as x tends to c from the positive side is fc, and the negative side is fc as well. Let's go and look at a new example. So let's look at the first example here. As x equals, as x tends to 0. Let's see whether it's continuous at 0. So if you take x and x tending to 0 from the positive side and from the negative side, let's look what happens. So we see limit as x tends to 0 from the positive side of fx. At this point, this is fx. We see that is equal to 1. And limit as x tends to 0 from the negative side, fx is equal to 1 as well. This is the second condition, and this is the third condition, and the first condition is f0 is equal to 1. So f0 is equal to 1, and this is equal to 1 as well as this is equal to 1. So this is continuous. So let's look at the next function. Here f0 is not defined. So the first condition is not satisfied. It's not satisfied, so it should be adequate to say that it's not continuous. But just we'll just for completeness sake, let's look at as x tends to 1 from 0 from the positive side and as x tends to 0 from the negative side. Limit x tends to 0 from the negative side is equal to 1, and 3, limit as x tends to 0 from the positive side, fx is equal to 1. Though these are equal to each other, since the function is not defined at fx was 0, this is not continuous. Let's look at one more example quickly. Here, let's take three conditions. Here we have f of 0 is equal to 2. F of 0 is equal to 2. That is, at 0 the function is 2. Then second one, limit of x tends to 0 from the positive side, fx as x tends to 0 from the positive side, we have a value of 1. And 2, 3, limit as x tends to 0 from the negative side fx is also equal to 1. So we see that the limit exists and the limit is equal to 1, but since all these three conditions are not satisfied, they are not equal, so this is not continuous. The limit exists, but it's not continuous. Let's look at this. First condition, f of 0, we want to see whether it's continuous at 0, so we take f0 is equal to 1. Then second condition, limit of x tends to 0 from the positive side of fx is equal to 1. Second, limit as x tends to 0 from the negative side is equal to, as x tends to 0 from the negative side is equal to 0. So we see that there is a value, but they are not equal. These two are equal, but these two are not equal. So it is not continuous. Let's look at one more example. This function, as f tends to 0, we want to see at 0, we have to, as f tends to 0, or when you substitute 0 to this function, we see that the denominator is 0, so this is not defined. So the first condition is not correct, not true. And this should be adequate to say that it is not continuous, but let's look at the other two conditions as well. Second, limit as x tends to 0 from the positive side, fx it goes to infinity, positive infinity. So it is also not defined. So if you look at the third condition, limit as x tends to 0 from the negative side, fx is negative, positive infinity. So this is definitely, this is a vertical asymptote, so this is not continuous around 0. Let's look at this. At function of f0 is equal to, is not defined, and as x goes to 0 from the positive side, let's say limit x goes to 0 from the positive side, fx is also not defined, because what it's doing is oscillating up and down as x goes to 0. So there is no number that it tends to, and even though it doesn't have a number, it does not tend to any number. So limit as x tends to 0 from the negative side, fx is not defined. So we see that the it's not continuous at x equals 0. So let's take another question. So here, when let's say is equal to fx, when first condition is fx f0, at f0 the function is not defined, but this should be adequate to say that it's not continuous at 0. So but let's look at the second, limit as x tends to 0 from the positive direction, from the positive direction, fx goes to positive infinity, whilst third, limit as x tends to 0 from the negative side, fx goes to negative infinity. So this goes to as x tends to 0 from the negative side. Let's look at one more question. here we see fx is equal to sine x over x. It is clear that as x is equal to 0, the function is not defined because there is a 0 in the denominator. So this would be the first condition. First condition is f0. We want to look at whether the function is continuous at 0 is not defined. So this is adequate to say that it's not continuous at 0. Then we'll look at, but we'll continue to look at limit as x tends to 0 from the positive side. Fx, we see from the positive side, it is equal to 1, and 0 from the positive side. This is approaching 0 from the negative side. And 3, limit as x tends to 0 from the negative side, fx is also 1. So we see that the limit exists, but it is not continuous because all three conditions are not satisfied. Let's go to one more thing. Here we see the function is defined as sine x over x when x is not equal to 0, and it gives a artificial value of 1 when x is equal to 0. So now this tells us that f at 0 is equal to 1, and limit from previous, we know x as x tends to positive from the as x tends to 0 from the positive side, 0 from the positive side and 0 from the negative side is equal to 1, and limit as x tends to 0 from the negative side is also equal to 1. So we see this is continuous because these conditions are satisfied. All three conditions are satisfied. So by taking a function and assigning values at places where the function does not exist, you can make the function continuous. In this example or in the exercise, they want us to check if the function is continuous between -1 and 3. So it is a close interval. So because it's square brackets, it is a close interval. Remember that square brackets represent close intervals. This means you have to make sure that it's continuous at the points specified here as well. So this is 0, -1, 1, 2, 3, positive 3 in x, 1, 2. So we have to, it's closed. Because it's closed, we have to check this point and this point. So those points should be included in the range. This would represent, circular brackets would represent open intervals, but square brackets represent close intervals. So since this is closed, we need to check all points including -1 and 3 to satisfy this condition. So let's take a different color for this. So we see that between 1, at 1 it's defined, at 3 it's defined, and between the functions 1 and 3 we see f2. f2 is not defined. So function at 2 is not defined. So if it's not defined, it is not continuous. So we can say that though the limit exists at 2 as x tends to 2 in the positive direction, x tends to 2 in the negative direction, limit exists, but it's not defined at 2. Let's look at 3. This second question, let's use a different color. In this second question, we see the function is defined all throughout except at 3. At function at f3 is about 1.5, 1.5. But as function of x, as x tends to 3 from the negative side, limit as x tends to 3 from the negative side, function is 1. So these two are not equal. Because this is not equal, this is also not continuous between -1 and 3. sorry, this should be square brackets. So let's take one more example. Here we see that the function includes -1 and includes +3 and has a value on every point along the graph. So it's all defined. So this is continuous. Let's look at this graph. We say if we look at -1 is defined, +3 is defined, but at x equals 0, if you look at function at 1, sorry, not 0, function at 1 is equal to 1. Function x at when x tends to 1 from the positive side, limit as x tends to 1 from the positive side is equal to 0, and limit as x tends to 1 from the negative side is equal to 1.5. So we see, sorry, at 1 is equal to 0. This is not 1, it's equal to 0. At 1 it's equal to 0. So these two are equal, but these two are not equal. So this is not continuous. Let's go to the next question. So this is a very interesting question. We are first asked to make a graph. So let's start looking at this part. So this function consists of 5 different graphs, and they vary in range. So let's look at first x squared. So x squared we have seen from some of the videos I made. X squared is a graph like this, y equals x squared. It's symmetric by the y-axis, this x squared. And if you want to plot x squared -1, that means it intersects at -1. So that would be a graph of this nature. -1 intercepts at -1. So we see a symmetric graph. This would be x squared -1. Let's look at the next graph, 2x. So 2x does not have an intercept, but it does have a gradient. If this is x, 2x would be of this nature, 2x, y equals 2x. So for every x, y is rises up twice as much. So y is equal to 2x here. Let's look at this graph over here. This is actually a point. When x equals 1, there is no variable here. So the point at 1, 1. So it represents a point, 1, 1. And then at and this graph, let me look at this graph. Let me look at this graph here. This is -2x. So it is -2x. It would be the negative of this. Maybe I should draw it somewhere here. So let me draw it here. So it should be the negative with the negative gradient, but it has a positive intercept. So first we'll draw the negative gradient. Sorry, that's wrong. It should intercept. So we'll first draw the negative gradient. So this should be y equals -2x, and then we have a positive 2. So it has to intercept at +4. So it would be a graph of this nature. Y equals -2x plus 4. Okay, and then we have fx equals 0. I'll use a different color for that. Fx equals 0. No, we have green. Let's use purple. So that is a graph of this nature. Y equals 0. That is that. X, y. So now we have to carefully select only the ranges represented by this area. So here this is -1 to 1. So that would be, let me highlight it in yellow. So that would be, or yeah, maybe highlight it in yellow or in light blue. So that would be this up to my and then the 2x would be from 0 to 1. So 0 to 1, and then at 1 it would be this dot, and then minus 2 is from 1 to 2. So that's 1 to 2 would be from here to here. Sorry, it's from 1 to 2. I made a mistake there. From 1 to 2 would be, I have to first draw the line. It's 1 to 2 in this graph actually. So it should be 1 to 2. Let's go here. It would be something like this, 1 to 2. And then 2 to 3 would be this part of the graph. So if you combine all these, it's not easy to see that, but if you combine all these, you will get a graph of this nature. This is the combination. You will see from minus 1 to 0 a graph like this, and here it does not include 0, so I'm going to put an open circle there. Then this is from 0 but does not include 0 to 1, and this is 2 to 1, and then it does not include this graph, and here we get 2, and we get a graph of this nature, that is this, and it does not include 2. If you see that, it does not include 2, it's less than 2, and then 2 to 3, it's a graph of this nature and does not include 3. So that's the graph. And let's say, what does f minus 1 exist? F minus 1, because it's included here, yes, f minus 1 exists. So f minus 1 has a value which is 0, and it is yes. Does x tends to minus 1 in the positive direction? Let's see what that it is. From the positive direction, 1 from minus 1 from the positive direction, it exists, yes, and it is equal to 0. Then minus 1 from the negative direction, positive direction, minus 1 from positive direction equal to minus 1. It is yes, because this is equal to this, and then we have this equal to this, and we see they are both zeros, so that is true, they are both zeros. Let's look at the next question. So here we are asked to find the limits as x tends to infinity. So what we need to remember here is, we know for a fact as 1 over x as x tends to infinity, 1 over x tends to 0. We know that for a fact. And 1 over x squared, x to the power half, 1 over x to the power half, whatever power it has, it all tends to 0 as x tends to infinity, Okay. So what we need to do is use this function and convert it into fractions of x, where x is in the denominator. So what we'll do here is divide it by the highest power of x. So we write it down, limit, this is equal to limit x tends to infinity, and we divide it by x squared. So we have 5 x squared over x squared plus 8x over x squared minus 3 over x squared over 3x squared over x squared plus 2 over x squared, right? So we can cross off the x squared terms because they are similar, and we can cross off 1x, this x we can cross off 1x there. Then we have a very convenient equation. Your limit as x tends to infinity, we have 5 plus 8 over x minus 3 over x squared over 3 plus 2 over x squared. So we see that as x tends to infinity, we see that this goes to 0 and this goes to 0 and this goes to 0. So we have an answer of 5 over 3. Let me answer the next question here. So as we'll take this also as x tends to infinity, we know 1 over x squared goes to infinity, 1 over x cubed goes to infinity. So we'll take this and divide it by the highest power of x, goes to, even if it's minus infinity, it's the same thing. So we divide it, then we get 11x over x to the power cube, because that's the highest power, plus 2 over x to the power cube over 2x to the power cube x to the power 3 minus 1 over x to the power 3. We divide the entire equation by x to the power 3. So then what we'll do is we will cross off the common factors, x to the power 3 and x to the power 3. Here one of the x's get cut off, so we get 2 here. So if we write this again, we have limit as x tends to minus infinity, we have 11 over x squared plus 2 over x cubed and 2 minus 1 over x to the power 3. As x tends to infinity, we know anything in the denominator, any powers of x in the denominator goes to 0. So this goes to 0, this goes to 0, right? And this goes to 0. So we are left with 0 over 2, which is equal to 0. Let's look at one more question. So in this question, let's divide the page into 4. And in this question, we see that if you substitute x equals 2, the new denominator is 0, and that means the function is not defined. But if we factorize it, let's see whether we could factorize it. We might be able to get away from that problem. So if we factorize, x squared minus 4 can be factorized as x minus 2, x plus 2, because this could be written as 2 to the power 2, and then we have this can be written as x minus 2 times x minus 2, and we can here cross off the negatives and then we have limit as x tends to 2, we have x minus 2 over x plus 2. So as x tends to 2, we see that we can still assign values. So what we get here is we get a 0 over 2, and this means any value over 0 over any value gives you a 0. Let's go to the next question. So the next question, we can, if you substitute 0 again, we get a 0 here. So but we can get the limit as x tends to 0, and we can factorize this just like we did here. So we get x minus 2 and x plus 2 and 1 x minus 2 here, and we can cross these off. When we cross this off, we get limit as, sorry, this shouldn't be 0, this should be 2. As x tends to 2, we have 1 over x plus 2, and now we can substitute 2 because this is not 0, so we get 1 over 4 here. So let's start with this. If we substitute, though it's 2 x tends to 2 in the positive direction, if we substitute 2 here, we are in trouble. This tends to 0. So what we can do is we'll try to factorize it, because it can be factorized. As x tends to 2 in the positive direction, we see x minus 2, x plus 2 and x minus 3. So unfortunately we cannot cancel any of these. So because we can't cancel any of these, and when you substitute 2 in the positive direction, one of these tend to 0, this limit is not defined, so it goes to infinity. So it is the values are not defined at x equals 2. This function is not defined as x equals 2. So let's look at the next question. Next question is similar, but it is limit as x tends to 2 in the negative direction. So we have x minus 3, and we can factorize this as x minus 2 and x plus 2. And as it tends to from the negative side, we see that the denominator is still 0. We can't cross off any of the terms, so we say it tends to infinity. So here what we see is then when x is equal to 2 and x is equal to minus 2, it's shown here, there are vertical asymptotes. So if this is 0 and we have 2 here and minus 2 here, we have vertical asymptotes here. So the function tends to infinity at minus 2 and 2, and it's the same in this case. Let's do one more question. And in this equation we say as x tends to 2, 2 minus x, x minus 2. So if you substitute x minus 2 here, x equals 2 here, we get a 0, and I don't think we can get away with that. So let's see, limit x tends to 2, and we can take a negative sign here and make it x minus 2, so that we can cross off at least one term. So x minus, it can be written as x minus 2, x minus 2 and x minus 2. We can cross off one term, but still we are left with 2 terms. So we have, after crossing off some of the terms, we have minus 1 over x minus 2 and x minus 2. So we see that as x tends to 2, the function is not defined. It goes to infinity. I hope you like this video. If you have any questions, please comment in the comment section.